Okay, now, it's 13 in European time. So we are going to start the best poster presentation session. And first speaker of this session is Dr. Naritaka Oshita. He's going to tell us about black hole ringing and overtones. Naritaka, please start.
Uh, Thank you very much, and thank you for giving me an opportunity to introduce my recent work. So I just submitted my paper on archive last week. Then yeah, I'll talk about this this time. So this talk is related to the previous talk by Professor Chukowskis given in the first day of this conference. And for more details, yeah, please look at this paper. But okay, so let me begin with the very brief introduction on quasinormal modes. So yeah, so as you know, the quasinormal modes are ubiquitous on the Earth and even in the universe. So bridge molecules and Earth and even stars have their own quasinormal modes, and those are very important in physics. So of course, black hole also have its own quasi-normal modes, and the quasi means that there's a damping in the normal modes. So this 1 over tau n represents the damping rate, and the Fn is the typical frequencies of the black hole. Then each black hole have infinite numbers of the quasi-normal modes. Then the interesting thing is that the damping rate and the frequency are determined only by the mass and angular momentum by virtue of the Noether theorem. So how can we observe the ring-down signals? For example, if we look at the rate-time signals of the GW signal emitted by the binary black hole merge events, you can find that. Then you can see the damping oscillations at rate times, and this is nothing but the signal emitted during the relaxation process of the black hole. Then this ring-down signal is a superposition of quasi-normal modes of the black hole. Okay, so as I said, there are infinite numbers of the quasi-normal modes as like this. For example, if you look at the quasi-normal frequencies for the spin parameter of 0.8 as like this, then here the horizontal axis is the real part and the vertical axis is the imaginary part of quasi-normal modes. Then the real part is a frequency Fn, and the vertical axis represents the damping rate 1 over tau n. Then this mode is called fundamental mode. Then this mode is the least damped mode of the quasi-normal modes, and at rate times, this fundamental mode is the most important, since at rate times all other quasi-normal modes called overtones are strongly suppressed at rate times. So only the fundamental modes survive at rate times. So you might think that then the other overtones are less important in the context of the GW observation. But actually, this point is now controversial. Okay, so this is related to the talk by Professor Chukowskis. So it was thought that the ring down starts at rate times, where the fundamental mode dominates the signal. But as go back in time, other overtones grow and could overwhelm the fundamental modes. Then at the strain peak, they argue that overtones are highly excited. And this claim is supported by the fitting data analysis, and there are a few strong supporting evidence for that. So Professor Chukowskis explained this as well in his talk. So I will briefly introduce their work. So they in this paper they performed the fitting of quasinormal modes to the raw data of the GW150914. Then so if you use the inspire, merger, and ring down phase, you can estimate the final spin and the mass with higher precision, like this. However, in this paper, they did not use inspiral phase. They just used the ring down phase. But they used the signal starting at the strain peak and also take into account the first or second up to second overtones. Then the result is this one. So once you take into account the first overtone, the result, the prediction for the spin and the mass are very consistent with that predicted by the inspire, merge, and ring down phase. So this is one of the strong supporting evidence for the claim. And this is another one. So they also tried the similar fitting data analysis for clean data produced by numerical relativity. Then they fit the first 8 quasinormal modes to the numerical relativity waveform and estimate the amplitude for each quasinormal. Okay. Then they found out that the fourth and fifth overtones are the most significant overtones. Recently, other group also reported that the similar results. So fourth and fifth overtones are very significant, and this result and the hierarchy among the overtones are insensitive to the initial conditions of the binary black hole merges. So they changed the phi in it, and this is one of the parameters of the initial condition of binary black hole. So here is the question. So why the fourth and the fifth overtones so special? And why the ring down can start as early as the strain peak or even before that? Those claims and these results are supported only by the fitting data analysis. So if this is true, this is very important result, since that means we can measure the remnant parameters of the black holes only from the ring down phase, for example, then with the higher accuracy than expected ever. Okay, so this is very important if that's true. But this statement is mainly supported by the fitting data analysis. We need more theoretical reason or evidence to support the claim or this result. That's my big motivation to work on this. Okay, so before moving to my recent work, so I like to emphasize this point. So so the quasinormal modes are characterized by frequencies and damping rate. In other words, the real part and the imaginary part of the quasinormal frequencies. But not only the frequency and damping rate, but also the ease of excitation of each quasinormal mode also characterizes the quasinormal modes. So each quasinormal mode has its own ease of excitation. Then this can be estimated by the residue of the poles of the black hole Green's function. Nowadays, it's known as the excitation factors, and this excitation factor is independent of the initial perturbation of the black hole. So this excitation factor quantifies the ease of excitation are determined only by the mass and spin of the remnant black hole. So this is very universal and a very useful quantity to quantify the ease of excitation. So not only the quasi-normal frequencies, but also excitation factor is important to characterize the quasi-normal. So the idea is very simple actually. So just compute the excitation factors up to higher overtones. So, okay, then so in order to obtain the ring-down signals, you can just perform this integral based on the perturbation theory of black hole. Then the first one is spin-weighted spheroidal harmonics. Roughly speaking, it's like spherical harmonics, but it's now Kerr black hole, so the shape is spheroidal, so yeah, it's a bit complicated. And this one is a black hole Green's function, and the third one is a source term. Then the Green's function of black hole have the infinite number of the poles, so roughly, so equivalently, the Green's function has a quasi-normal modes, as a poles. So by using the residue theorem, this integration reduces to the summation over all the poles of the Green's function, and each poles are numbered by the overtone number n. So that's why we have to perform the summation over the overtone numbers. Then each amplitude for the quasi-normal modes are given by the product of the excitation factors and the source factors and the spheroidal harmonics. Then again, all of the information of the initial condition is encoded in the source factors. And on the other hand, excitation factors is completely determined by the structure of the black hole's Green's function. So any information about the initial condition any information about the initial condition are absent in the excitation factors. This is determined only by the mass and spin. Then this is the explicit form of the excitation factors, and A out and A in can be obtained by the homogeneous solution of the homogeneous Chukowskis equation. It's here. Right. So in principle, just solving the Chukowskis equation, we can compute the excitation factors. Although there's a few technical difficulties, but yeah. Then, okay, so in summary, okay, so now now if we look at the L equal M equal 2 mode, that is the most dominant harmonics in the ring down induced by the binary black hole margin. Then the each amplitude for each quasi-normal mode is determined by the product of two factors now. So e to 2n, that's the excitation factors independent of source perturbation. And the t to 2n is the source factors, and all information about the initial data are encoded there. Then this is a result of the excitation factors, just computing by solving the Chukowskis equation. Then J is the non-dimensional spin parameters. So the GW data analyzed by the previous work has the J is equal to almost 0.7. So we can look at this one. So you can see that fourth and fifth overtones have the first two highest excitation factors. So this is just prediction from the Green's function, and I didn't use any information about the binary black hole mergers or something like that. Yeah, but the excitation factors predict the fourth and the fifth overtones are important. Okay, then this is very consistent with the results obtained by the previous work. They also reported that the fourth and fifth overtones are very important. This is very amazing since just looking at the Green's function, the structure of the Green's function, we can predict the importance of overtones. However, yet we have to be careful since the amplitude of each quasi-normal mode is determined by the product of two factors, not only this one. The source factor is also important. So we can't ignore the source factors. We have to look at the behavior of the source factors as well. Okay, but the computing the source factors for the for example, binary black hole merge events is highly challenging since it involves a highly nonlinear regime. Okay. But now, in the previous work, they extracted the excitation coefficients by using the fitting data analysis of the numerical relativity waveform. Then now, looking at the Green's function and the structure around the poles of the Green's function, I computed the excitation factors up to 20 overtones actually. So now it's very simple. Just compute the C2 to N divided by E2 to N. Then we can compute the source factors even for the binary black hole merge event. That's super easy now. So this is the results. Then now I show you the E2 to N over E2 to naught, and the red lines T2 to N over T2 to naught. So this is just I want to show you the dependence of the excitation factors and the source factors on the overtone numbers. So this now of course this is 1, but 4, 9, 16, 23, and around 24 or 25 or so. So it changes by the factor of 25 or so at most. But in the last line, speaking of the source factor, it's just 1, 1, 1.2, 1.4, 1.4, something like that. So almost order of the unity. So we can say that the excitation factor is very sensitive to overtone numbers. But the source factor of the binary black hole merger is insensitive to the overtone numbers. So in other words, to discuss the importance of overtones, actually the source factor is not so important than the excitation factors. So to see the importance of the overtones, the excitation factor, we should know the behavior of the excitation factors. Okay. Then the excitation factor are independent of the initial conditions and determined only by the spin and the mass of the remnant black holes. So this is a very, powerful statement actually. But of course, now I just show you the one sample. So we have to look at other GW waveforms by changing the many initial conditions of the binary black hole. Yeah. Okay. Then so although I did not mention about the spheroidal harmonics, but Actually, this also determines the amplitude of each quasi-normal mode. Okay. Then the question is the same thing for the source factors. Is this sensitive to the overtone numbers or not? Oh, sorry. And then so this is actual result. So I again show you the S22N divided by S22 naught. Then it's from the 0.9 to 0.2 or more. So yeah, the spheroidal harmonics is also insensitive to the overtone numbers, as like this. So indeed, the excitation factor only is important, to discuss the importance of overtones or the significance of the overtones. Well, so why? I think some of you might wonder why the fifth overtone is so special. So for as you can see, the fifth overtone has the highest excitation factors. But why fifth overtone is so important? So I don't know, but now I found a very interesting coincidence between the peak of the excitation factors and the quasi-normal curves, actually. Okay, so let's compare between them. So this is the excitation factors, and now the red point indicates the overtones at which the excitation factors takes the peak value. Okay, then now I'd like to compare this with this one. So quasi-normal frequencies. Then now vertical axis shows the real part of the quasi-normal modes, not the excitation factor, quasi-normal, just quasi-normal frequencies, real part. Then the horizontal axis is the overtone numbers, up to 20s. Then, okay, so then now the red point again indicates the overtone number at which the excitation factor takes the maximum value. Like this. Here. Oh, yeah. So as you can see, so you can see that the real part of the quasi-normal modes have the kind of corner, right? There's a corner, and at which the excitation factors takes the maximum value. Yeah. So this is a very interesting coincidence, but I don't know why. So that's why I don't know. But this is a very interesting and important, since this implies that there is a meaning in the corner of the quasi-normal frequencies, and this is very important to see the significance of the quasi-normal mode. Yeah, the ease of excitation of the quasi-normal mode. Then, okay, so now, okay, so the next question is that, so running the spin parameters of the curve black hole, then running the overtone numbers, so where is the maximum value of the excitation factor? So in other words, at which parameters can we obtain the most, the easiest modes to excite? Okay, so then to explain this, let me briefly explain the anomalous behavior of the fifth quasi-normal frequencies. So this now I show you the quasi-normal frequencies running from the spin parameter of 0.85 to 0.95. Then obviously the fifth overtone is special. Again, I don't know why, but it is what it is. So then the zooming up and zooming up, there's a the loop trajectory like this around the spin parameter of 0.9 Actually, the Onozawa in 19, sorry, I forgot, found this anomalous behavior first. But yeah, so anyway, around 0.9 spin parameters, there's anomalous trajectories of the quasi-normal frequencies for fifth overtone. Okay, at the 0.9, what happened in the excitation factors? So the actual nth overtone also takes the maximum value in the excitation factors. So around the spin parameter of 0.9, then the fifth overtone has the highest excitation factors. So if you find the binary black hole merger whose remnant has the spin parameter of 0.9, maybe fifth and sixth overtones could highly excited. Yeah, that's just a prediction from the Green's function of black hole. But also, I don't know why this is interesting in the context of the astrophysics, but approaching to the extremal limit, the opposite situation comes. So fifth overtone is highly suppressed, strongly suppressed at the extremal limit. Okay. So what happened in the quasi-normal frequencies? Yeah, actually, the fifth quasi-normal modes are isolated from other quasi-normal modes. And in this situation, the fifth quasi-normal mode is harder to excite. Okay. Yeah, so there are many mysteries in the quasi-normal modes, even in GR. I don't know why the fifth overtone is so special, but yeah, this is very interesting. And perhaps looking at the Kerr CFT correspondence, for example, where the Kerr perturbations correspond to the CFT degrees of freedom, there might be a nice answer. I don't know, but yeah. Anyway, there's the mystery of the fifth overtone here. Okay. So now, yeah. So although we looked at the very interesting behavior of the quasi-normal modes, but to confirm these findings from independent way, I computed the GW signal induced by a particle passing into a spinning black hole. Then, yeah, this is the result. So then I also changed the initial condition of the infalling particles as like this to see the universality of the importance of overtones. Then I performed the fitting analysis for that. Then yeah, so 4.7, yeah, so fourth and fifth overtones are highly excited again. Then the 4.9, yeah, fifth, sixth overtones are highly excited. The interestingly, yeah, 4.99, almost extremal limit, fifth overtones are highly suppressed, as I showed you in the previous slides here. And again, the excitation factor dominantly determines the importance of overtones, and other source terms are not so significant to determine the importance of overtones. Okay, so maybe this is the final slide. Well, okay, so now in my recent paper, I introduced a new quantity. I call it the decay time. Then this tells us when the nth quasi-normal modes tends to be less important than the fundamental mode. So this is a rough schematic picture. So okay, so now I show you the in the log scale. I show you the amplitude of each quasi-normal modes. Right. Then as goes to the higher overtones, the suppression becomes strong. But on the other hand, as early times, the higher overtones becomes more significant. Then now question is, when does the nth quasi-normal mode becomes less important? Then this can be quantified by this intersection point. Okay, so blue line is the amplitude for fundamental quasi-normal modes. Yeah. Then now I define the decay time as like this. Then this means that now I suppose that the amplitude of each quasi-normal mode is exactly given by the excitation factors only. Then in this case, when the nth quasi-normal modes becomes less important, that's the question. Then this can be given by this one. Okay. Then this is I think a very nice quantity to quantify the in realistic case. Of course, this is not the case. The source factors or the source factor exists as well. So there's some deviations. But if source factor is less important, in other words, is insensitive to the overtone numbers, this quantity may grasp the essence for this equation. Then so anyway, I computed the decay time for various spin parameters as like this. Then now the star markers is computed by is actually slightly different from the this definition. Here, actually in the previous work, they obtained the excitation coefficients. They obtained the amplitude for each quasi-normal mode by using the fitting data analysis. Then by using the real amplitude, I computed the when the nth quasi-normal modes tends to be less important. Then those are well matched. Then this signal corresponds to the final black hole of spin parameter 0.7 roughly here. So there's a deviation from the 0.9, but yeah. Anyway, this is very consistent with 0.7 or 6 or 8 or Actually, this decay time is insensitive to the spin parameter in the range of the 0.6, 7, and 8. Anyway, okay, so let me summarize my talk. Okay, so so the original claim is very important anyway. So if the ring down signal is excited as early as the strain peak or even before the strain peak, we can measure the remnant parameters with higher accuracy. And we can test actually they indeed did that, but we can test the no-hair theorem of black hole out of the GW signals. That's a very nice thing. And then but those claims are supported only by the fitting data analysis. So in this work, I computed the excitation factors by looking at the Green's function of the black hole. Then the prediction from the excitation factors is well consistent with the result from the fitting data analysis. And I also computed the source factors by combining the result in the previous work and my current work. Then then the results say that the source factor is insensitive to the overtone numbers. And interestingly, this is an academic interest, but fifth excitation factor is very anomalous. No, the fifth or quasi-normal mode is anomalous. So speaking of the excitation factor, it's suppressed in the near extrema, and it has a peak at spin parameter of 0.9. And the decay time is very useful to predict when the n quasi-normal mode tends to be less important than the fundamental mode. Okay, so thank you very much.
Okay, Naritaka, thank you very much for your interesting talk. And now session is open for question and comments. So Shinji, yeah, please ask.
Yes, thank you for the very nice talk. Very clear. And so from the last picture, last plot, can you say that up to which which overtones do you need to approximate the actual waveform? I think on Monday something like a 7 is enough.
Yes, 7 is enough.
I see.
Yeah.
From this you can say.
Yes, I agree with that. Yeah. So actually, okay. So maybe I think this graph is nice. So okay. So fourth, fifth has highest excitation factors, and sixth, seventh, and so starts to decrease. And so that's why seventh, or some authors say that sixth quasi-normal mode is enough, but around 6 or 7 is enough. And eighth or ninth also can be important compared to the fundamental mode, but those are highly suppressed, so suddenly disappear. So
I see.
Yeah, so impractical. Yeah.
Again, source term is not important for this aspect. I see.
Yeah, seems right. So yeah.
Okay. Yeah. Thank you.
Okay, and Chaeyu Chen from the audience. Look, how to invite?
Yes, I can speak.
Yes. Okay, please.
Okay, so actually I have one question and one comment. And the first question is that it seems that in your slides you only show the case of black hole with non-zero spin. So I'm just curious, does this n equal to 5 overtone still have the largest excitation factor for non-rotating black hole?
That's a good question. Yeah, thank you very much. Yeah, so there's a reason that I did not show the 0.2 or 0.1 or even 0. Yeah, so okay, so to explain this, actually I have to explain how I computed the excitation factors. Okay, so anyway, as I said, to compute the excitation factors, we have to solve the Chukowskis equation. Then to look at the higher overtones, we have to solve the Chukowskis equation in very high precision. It's super difficult, but recently, actually Maple also did have the function. But so let's forget about the Kerr black hole. So Kerr-de spacetime and the perturbation of the Kerr-de spacetime, of course, and the Chukowskis equation exists. Then the Chukowskis equation for Kerr-de spacetime has the analytic form of the solution. Then now I used the analytic solution of the Kerr-de spacetime. Then in the Kerr-de spacetime, I computed the excitation factors almost semi-analytically. Then computed the very small cosmological constants. Then I extrapolated to the lambda equals to 0 value. Then I obtained the excitation factors of the Kerr black holes. however, in order to extrapolate to lambda equals to 0, we have to specify the right proper fitting function. However, this line has some modulation in this very slow rotation limit. So, and it's hard to extrapolate to lambda equals to 0 for lower spin cases. So that's why, yeah, actually I didn't compute the excitation factor for lower frequencies, sorry. Yeah. Sorry, did you see
I see, yes, I understand. So actually I have another comment, but I don't know whether I still have time. Can I?
Yeah, please make it quickly, yeah.
Yeah, sure. So basically, since you point out that the importance of this higher overtone, so maybe it would be very interesting to connect this idea with the recent development of pseudo spectrum, which was actually proposed by Jose Luis Jaramillo and also by Vito Cardoso very recently. And this can be very useful in particular in testing gravitational theories. And they also mentioned there could be some instability spectrum for higher overtones. Yeah. Oh. So that's just a comment.
I see. Okay, thank you very much. Thank you.
Okay, so now time is almost running out. So yeah, let's thank the Naritaka again.
Thank you very much.
Yeah, and